We have a peculiar habit as a species. We stand on the solid ground of our planet, a sphere of rock and metal hurtling through the cosmos at 100,000 kilometers per hour, and we look up. We stare into the endless, cold black, and we dream of conquest. We've sent our robotic emissaries to the rusty plains of Mars, to the swirling, toxic clouds of Jupiter, and to the ghostly methane seas of Titan. Our telescopes have peered back to the very dawn of time, capturing the faint, residual glow of the Big Bang itself. We have mapped galaxies billions of light years away, and yet there is a territory far closer, yet infinitely more hostile, that remains utterly beyond our grasp. A final frontier that isn't out there, in the void, but right here, directly beneath our feet. We live on the impossibly thin skin of an apple, blissfully unaware of the cataclysmic furnace raging within. The longest journey humanity has ever conceived is not to Alpha Centauri, not to the Andromeda Galaxy, but downward, a mere 6,371 kilometers. A journey to the center of the Earth, and it is, without exaggeration, the single most difficult, most audacious, and most profoundly impossible engineering challenge we have ever faced. It makes landing on the moon look like a practice run. It makes colonizing Mars seem like a weekend camping trip, because this isn't a journey through the sterile vacuum of space. It's a descent into a literal inferno, a place where the laws of physics as we know them are twisted into monstrous new forms. We are detectives, and our planet has presented us with the ultimate locked room mystery. The room is its own core, and the walls are 6,000 kilometers of unimaginable pressure and heat. The question that has haunted engineers and dreamers for centuries isn't just what's down there, but the far more fundamental question that drives our channel. How in the world could we ever build a machine to find out? What kind of impossible materials, what kind of unheard of physics, what kind of outrageous ingenuity would it take to crack the code of our own world? Let's begin our investigation by mapping the crime scene. The sheer scale is the first clue to its impossibility. Our journey begins by piercing the Earth's crust. This is the part we know, the familiar ground. On a planetary scale, it's thinner than paper. At its thickest, under the great mountain ranges, it might reach 70 kilometers. Under the oceans, it's a scant 5. Humanity's most ambitious attempt to penetrate this layer was the Kola Superdeep borehole, a triumph of Soviet engineering that clawed its way into the Baltic Shield for 2 decades. The result? A hole just over 12 kilometers deep. 12 out of more than 6,000. We barely scratched the paint. The project was abandoned, not for lack of funding or political will, but because the engineering simply failed. At 12 kilometers, the temperature was already 180 degrees Celsius, twice what they had predicted. The rock, under that modest pressure, behaved less like a solid and more like a plastic. The drills became useless. Our most powerful machines were defeated before the journey had even truly begun. It was a humbling lesson. The Earth does not give up its secrets easily. And that was just the crust, the kindergarten level of this challenge. Beneath this fragile shell lies the true monster, the mantle. This single layer accounts for more than 80% of the Earth's volume. It is a realm of silicate rock, stretching down for nearly 3,000 kilometers. To call it rock, however, is a profound injustice to the bizarre state of matter that exists here. We are taught in school that the mantle is molten, a sea of magma. This is not quite right. It's a state called viscoelasticity. Think of a glacier. It's solid ice. You can walk on it, you can hammer it, but over geological time, it flows. It carves valleys. The mantle is like that, but on an unimaginable scale and under pressures that are difficult to even conceptualize. At the top of the mantle, the pressure is already thousands of times greater than its sea level. By the time we get to the bottom, it's over 1.3 million times. Atmospheric pressure, 1.3 million. Let me try to give you an analogy for that. Imagine the entire weight of the Eiffel Tower. Now, balance it perfectly on the tip of your thumb. That is roughly the pressure a submarine experiences at the bottom of the Marianas Trench. Now, take 100 of those Eiffel Towers and balance them on that same thumb. You are still not even close to the pressure at the base of the mantle. No material we have ever synthesized can withstand this. It doesn't just bend, or break, or melt. At these pressures, the very atomic structure of matter is crushed and rearranged into new, exotic forms. A vessel trying to traverse this would need a hull made not of matter, but of a controlled scientific miracle. And all the while, the temperature is climbing from 1,000 degrees Celsius near the crust to over 4,000 degrees as we approach the next boundary. This is a heat that makes steel flow like water. And after 3,000 kilometers of this crushing, searing, flowing rock, we arrive at the next great wall, the boundary between the mantle and the outer core. Here, the game changes completely. We leave the world of rock and enter a world of metal. The outer core is a vast, turbulent ocean of liquid iron and nickel, nearly as large as the planet Mars. The temperature here leaps to 5,000 degrees Celsius, hotter than the surface of our sun. The pressure is now over 3 million atmospheres. But the true challenge here is not just the heat or the pressure, but the motion. This is not a calm ocean. It is a maelstrom of molten metal, churning with violent convection currents at speeds of kilometers per hour. This swirling inferno is the engine of our planet. It is the dynamo that generates Earth's magnetic field, the invisible shield that protects us all from deadly solar radiation. For a vessel, this is an electromagnetic nightmare. It would be tossed about by currents of liquid metal while being subjected to magnetic forces of incredible power, frying any conventional electronics and possibly even tearing the ship apart. How do you navigate a sea of lightning and lava? How do you propel yourself through a planetary-scale electrical generator that is actively trying to destroy you? We would be deaf, blind, and utterly lost in a tempest of our own planet's making. If, by some physics-defying miracle, our craft survives the liquid outer core, it would arrive at the final destination, the ultimate prize, the Earth's inner core, a solid sphere of iron and nickel, about the size of the moon, suspended in the heart of the liquid maelstrom. And here lies the final, most profound paradox of our journey. The temperature in the inner core is estimated to be 6,000 degrees Celsius. It is staggeringly, incomprehensibly hot. And yet, it is solid, a solid ball of metal hotter than the surface of the sun. Why? Because the pressure has finally reached its zenith, nearly 4 million times the air pressure at sea level. The pressure is so immense, so cosmically powerful, that it overwhelms the thermal energy. It forces the iron atoms into a fixed, solid lattice, preventing them from melting, no matter how hot they get. This is the heart of our world, a place of cosmic violence, where the fundamental forces of temperature and pressure are locked in an eternal, planet-forging battle. To land on this surface, to take a sample, would be the greatest achievement in the history of exploration. But it is so far beyond our capabilities that it belongs in the realm of mythology. So this is the map of our impossible descent. It is a journey that attacks any conceivable machine on 4 fronts. First, the crushing pressure, which would atomize any known substance. Second, the searing heat, which would vaporize any cooling system we could design. Third, the problem of propulsion through mediums ranging from plastic-like rock to liquid metal. And fourth, the complete impossibility of communication or navigation through thousands of kilometers of dense, chaotic matter. We are faced with a challenge that cannot be solved by simply building a stronger hull or a more powerful engine. Brute force engineering is a non-starter. This problem is too fundamental, too extreme. So, what is the answer? Do we simply resign ourselves to the fact that our own planet's heart is forever beyond our reach? Or have we been asking the wrong questions? What if the solution isn't to fight against these colossal forces? What if the key to cracking the code isn't to build a vessel that can resist 4 million atmospheres of pressure, but one that somehow ignores it? What if the answer to surviving 6,000 degree temperatures isn't to build a better shield, but to find a way to not be there at all. The enigma of this journey, the true thesis of our investigation, is this: to conquer the inner world of our planet, we may need to stop thinking like terrestrial engineers and start thinking like cosmic ones. The clues to solving this impossible descent may not be found in metallurgy or mechanics, but in the deepest, most exotic corners of theoretical physics. The journey down, it seems, must begin by looking up. In any great investigation, before you can find the solution, you must first understand the true nature of the problem. You must respect the adversary. And in this case, our adversary is the planet itself. The introduction gave us the map of the crime scene. Now, we must analyze the weapons. The physical laws that make this journey not just difficult, but statistically indistinguishable from a suicide mission. We are not fighting monsters or aliens. We are fighting the fundamental forces of the universe, weaponized by sheer scale. Let's open the case file on what we'll call the catastrophe cascade, because the failure of this mission isn't caused by a single fatal flaw, but by a series of interconnected, mutually reinforcing impossibilities. Each challenge feeds and magnifies the next, creating a fortress of physics that has, until now, proven utterly impregnable. Our analysis begins with the most obvious, most brutal, and most absolute of these challenges: the pressure. Case File 1. The pressure singularity. We use the word pressure in our daily lives, but we have no true context for what it means in the heart of a planet. At the bottom of the Mariana Trench, the deepest point in our oceans, the pressure is about 1,100 atmospheres. It is enough to crush a military submarine like a soda can. It is a formidable engineering challenge, but one we have solved. We have built remotely operated vehicles that can survive it. Now, take that pressure and multiply it, not by 10, not by 100. To reach the Earth's inner core, we must withstand a pressure of approximately 3.6 million atmospheres. It's a number so large it loses meaning. Let's be methodical. The strongest material we can mass produce is high-grade steel. Its compressive strength is around 2 gigapascals. The pressure at the core is 360 gigapascals. Our best steel is, therefore, 180 times too weak. What about something more exotic? Tungsten carbide. Still not even close. What about the hardest known natural material, the diamond? A diamond's compressive strength is formidable, but it too has a breaking point. And under the conditions of the deep mantle and core, diamond itself is no longer stable. Its crystalline structure would be crushed and rearranged into even denser forms of carbon. We are facing a force that doesn't just break materials. It rewrites their fundamental nature. So the obvious brute force solution is to just build thicker walls. This is where engineering intuition fails and the unforgiving math takes over. The strength of a hollow sphere against external pressure does not increase in a simple, linear way with its thickness. Worse, the weight of the vessel increases with the cube of its radius. This means a vessel with walls twice as thick would be more than 8 times heavier. To build a sphere capable of resisting the core's pressure using any known material, its walls would have to be absurdly thick, so thick, in fact, that there would be no room left inside for a crew, for instruments, or even for a hollow space. You would essentially be building a solid ball of metal. More critically, the structure would become so massive that it would collapse under its own gravity and the immense forces acting upon it long before it reached its destination. We cannot build our way out of this problem. The very concept of a hollow vessel with a survivable interior is a physical impossibility. The pressure doesn't just want to crush the hull. It wants to annihilate the empty space within it. Nature abhors a vacuum, and in the center of the Earth, this is not a turn of phrase. It is the supreme law. Any empty space is a flaw, an invitation for catastrophic failure on an atomic level. To survive, the pressure inside the vessel would need to perfectly match the pressure outside. And no biological life, no delicate electronic sensor, can exist when it is being squeezed by the weight of a planet. This weapon, pressure, presents a complete and total checkmate, or so it seems. Case File 2, the thermodynamic wall. Let's assume for a moment that we solve the pressure problem. By some miracle of future science, we invent a material or a force field that can create a stable bubble of space for our journey. The moment that problem is solved, its sibling moves in for the kill, the heat. The Earth's core burns at 6,000 degrees Celsius, a temperature that again is hotter than the surface of the sun. The challenge is not merely surviving this heat, but the fundamental laws of thermodynamics that govern it. In the vacuum of space, a spacecraft has a huge advantage. It is surrounded by the near absolute zero of the void. Heat can be radiated away. It's a complex problem, but there is always a cold sink, a place for the heat to go. On our journey, we have the opposite problem. We are a relatively cool object, say 20 degrees Celsius inside, descending into a 6,000 degree furnace. The second law of thermodynamics is now our executioner. It states unequivocally that heat will always flow from a hotter region to a cooler one. Our vessel is the cooler region. The entire planet around it is the hotter one. Heat will pour into our ship from all directions, relentlessly, through conduction and convection. How do we fight it? The first thought is insulation. But there is no such thing as a perfect insulator. Given enough time, heat will always get through. Our journey would take weeks, if not months. The best insulators we have would be vaporized in an instant. The next idea is active cooling. This is how a refrigerator works. It uses energy to pump heat from the inside of the box to the outside. But this only works if the outside is cooler than the system's radiator. Where do we pump the heat? We are surrounded by a medium that is thousands of degrees hotter than our own engines waste heat. It's like trying to bail water out of a boat that is already at the bottom of the ocean. Any cooling system we could design would be a heat pump working in reverse, actively sucking the inferno from the outside into our vessel and accelerating our demise. What about ablative shielding, the kind used on atmospheric re-entry vehicles? These shields work by literally burning away, carrying the heat of friction with the vaporized material. It is a brilliant but sacrificial solution. It works for the handful of minutes it takes to plunge through an atmosphere. For a journey of months through a medium that is constantly transferring heat to the hull, we would need a shield thousands of kilometers thick. We would have to build a ship the size of a moon to carry its own sacrificial heat shield. The thermodynamic wall is absolute. We are a single ice cube thrown into a star. Melting is not a risk. It is a mathematical certainty. Case File 3, the labyrinth of motion and sensation. With the pressure and heat problems having seemingly crushed and incinerated our mission, let's add a third layer of impossibility. How do we move? And how do we know where we are going? Let's start with propulsion. How do you drive to the center of the Earth? Through the solid and viscoelastic mantle, the only concept we have is drilling. As the Kola borehole proved, this is agonizingly slow, and the energy requirements are staggering. The deeper you go, the hotter and more plastic the rock becomes, gumming up and melting any drill bit we can conceive. The energy needed to drill thousands of kilometers would require an onboard power source far beyond anything we've ever built. A compact fusion reactor would be the minimum. But such a reactor would itself generate a tremendous amount of waste heat, compounding the thermodynamic problem to an absurd degree. Once we reach the liquid outer core, drilling is useless. We are now in a fluid, but this fluid is a churning ocean of liquid iron, denser than any magma, more viscous than water. Conventional propellers would be useless. They would melt instantly and provide little thrust in such a dense medium. Perhaps some form of magneto-hydrodynamic drive, using magnetic fields to push against the conductive liquid metal? It's a plausible concept until you remember that the core is already generating its own colossal and chaotic magnetic field. We would be trying to navigate a hurricane using a small handheld fan. This brings us to navigation and communication. On the surface or in space, we know where we are. GPS, star tracking, radio communication. All of these tools become instantly useless the moment we go underground. Radio waves, the foundation of all our communication, cannot penetrate more than a few meters of solid rock, let alone 6,000 kilometers of rock and liquid metal. The Earth itself is the ultimate Faraday cage. We would be completely, utterly cut off. No messages to the surface, no data transmission, no cry for help. We would be more alone than any human in history. And how would we navigate? Inertial navigation systems, which use gyroscopes and accelerometers, suffer from cumulative error. Even the most advanced systems, used by nuclear submarines, would be hopelessly lost after a journey of this magnitude. The tiny, unavoidable errors in their measurements would add up over thousands of kilometers until our perceived position was dozens, if not hundreds, of kilometers away from our actual one. We would be blind, deaf, and lost in the heart of our own planet. This is not just an engineering problem. It's a crisis of fundamental physics. There is no known way to see, speak, or navigate through a solid planet. The journey to the core is not a voyage. It's a blind, silent fall into oblivion. The challenges are not sequential. They are simultaneous. It is a symphony of failure, where every instrument of physics is playing in perfect, deadly harmony. So, the case is closed. The evidence presented in Phase 1 is overwhelming. The combined forces of pressure, heat, and isolation form a perfect fortress. Any conventional approach, any feat of brute force engineering, is doomed to fail. A vessel made of matter, no matter how strong, will be crushed and vaporized. A cooling system, no matter how efficient, will be overwhelmed. A propulsion system, no matter how powerful, will be rendered useless. This is the logical conclusion. The mission is impossible. And if we limit our thinking to the familiar scale of human engineering, that conclusion is correct. But the universe is not limited to our scale. The cosmos is the ultimate laboratory, constantly running experiments at energies and densities that dwarf our wildest imagination. And within that laboratory, there are clues. There are phenomena that treat the very forces that defeat us as mere playthings. To crack the code of our planet's core, we must first look for inspiration in the places where the laws of physics are pushed to their absolute limits. We are looking for loopholes. We are looking for precedents. We are looking for the universe's own solutions to impossible problems. Our first clue comes from the graveyards of giant stars. The neutron star. A neutron star is one of the most extreme objects in the known universe. It is the collapsed core of a star many times more massive than our sun. After a supernova explosion blows away the star's outer layers, the core collapses under its own immense gravity. It collapses past the point of being a white dwarf, where atoms are still intact. It collapses so far that the gravitational pressure overwhelms the forces that keep atoms apart. Electrons are squeezed into protons, creating a sea of neutrons. The result is an object perhaps 20 kilometers in diameter, the size of a city, that contains more mass than our entire sun. The density is beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons. The gravity is so intense that a marshmallow dropped on its surface would impact with the force of 1,000 hydrogen bombs. Now, what stops it from collapsing further into a black hole? What holds this impossible object together against its own ludicrous gravity? It is not material strength. It is a quantum mechanical principle known as neutron degeneracy pressure. Degeneracy pressure is a bizarre and powerful concept. It stems from a rule of the quantum world called the Pauli exclusion principle, which states that no two neutrons, or other similar particles, can occupy the same quantum state in the same place. As gravity tries to crush the neutrons closer and closer together, the neutrons push back, not with physical force, but with a fundamental quantum refusal to be in the same state. It is the universe itself saying, "This space is occupied." This is not a wall made of atoms. It's a wall made of a fundamental law of physics. This is our first major breakthrough. The universe's solution to near-infinite pressure is not a stronger material, but a more clever application of physics. It sidesteps the problem of material strength entirely. So, our first question as cosmic detectives is this: could we, theoretically, replicate this effect? Could we create a localized field or bubble around our vessel that exhibits a form of this degeneracy pressure? Could we create a quantum shield that doesn't physically block the pressure, but simply makes the space our vessel occupies fundamentally incompressible? We don't know how to do this yet, but the universe has shown us that it is possible. The precedent exists. The pressure problem may not be one of metallurgy, but of quantum field manipulation. Our second, and perhaps most profound, clue comes from an even more extreme object, the black hole. A black hole is where gravity has won the battle completely, crushing matter into a singularity, a point of infinite density. But the clue for us is not the singularity itself, but its boundary, the event horizon. An event horizon is not a physical surface. You could not touch it or stand on it. It is a boundary in the fabric of space-time itself. It is the point of no return, where the gravitational pull is so strong that the escape velocity is greater than the speed of light. The key insight here is that gravity, as Einstein taught us, is not a force in the conventional sense. It is the curvature of space-time caused by mass and energy. Massive objects like planets and stars create a dent in space-time, and other objects simply follow the resulting curves. This is gravity. This reframing is everything. If gravity is just curved space-time, then the heat and pressure within the Earth are properties of that specific region of space-time. They are bound to the fabric of the cosmos at that location. This leads us to the most important question of our entire investigation. What if we didn't have to travel through that region of space-time? What if we could, instead, travel by manipulating space-time itself? This brings us to one of the most tantalizing and controversial concepts in theoretical physics, the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, it is a theoretical solution to Einstein's field equations. It describes a way to travel faster than light without violating relativity. It works by creating a warp bubble of flat, undisturbed space-time around a spacecraft. The drive would then work by compressing space-time in front of the bubble and expanding it behind. The bubble itself, with the ship inside, would be pushed along on this wave of space-time. Crucially, the ship inside the bubble is not moving through space at all. It is stationary within its local frame. It is the space itself that is moving. Now, while this is typically discussed for interstellar travel, let's apply this concept to our subterranean journey. Imagine our vessel encased in one of these warp bubbles. Inside the bubble, space-time is flat. It is calm, cool, and at normal pressure. This bubble is our lifeboat. Outside the bubble, however, space-time is being violently warped by our drive, creating a wave that propels us downward. The 6,000-degree heat of the Earth's core? It would never touch our hull. It would be acting on the warped space-time boundary far from the ship. The 3.6 million atmospheres of pressure? It would be squeezing that boundary, not our vessel. Our ship would be completely isolated, a passenger in its own private universe, surfing down to the center of the Earth on a self-generated wave of gravity. This is a breathtakingly elegant solution. It doesn't just solve the heat and pressure problems. It annihilates them. It reframes them as irrelevant. The laws of thermodynamics can't boil us if the heat can't reach us. The limits of material science don't matter if the pressure is never applied to our hull. It would even solve the propulsion problem. We would no longer need to drill or push through rock and liquid metal. We would simply move the space we are in, and the matter that was previously there would be shunted around our bubble. We would pass through the planet like a ghost. And this is the critical next step in our investigation. This solution comes with a colossal catch. According to the mathematics, to create this space-time distortion, you need something that is not known to exist in our everyday world. You need exotic matter, specifically matter with a negative energy density. In simple terms, you need matter that has anti-gravity properties. It would be pushed by gravity, not pulled. It would fall up, not down. We have never held a lump of this matter in our hands. Its existence is purely theoretical, and yet the universe gives us clues here too. In the strange world of quantum mechanics, in phenomena like the Casimir effect, we see hints of negative energy densities existing for fleeting moments in the quantum foam. The clue is not a substance, but a possibility. The physics does not forbid it. Our investigation has given us a theoretical key to unlock the Earth's core. The question now becomes, can we find the impossible material required to forge that key? This is the turning point in any investigation. It is the moment when the scattered clues, the impossible facts, and the wild theories suddenly snap into focus. We have a perfect problem, the impenetrable fortress of the Earth's interior, and we have a perfect theoretical solution, the warp bubble, a pocket of isolated space-time that could bypass the dangers entirely. But this solution hangs on a thread, a single seemingly unobtainable ingredient, exotic matter with negative energy density. This is where most investigations would end. In a file labeled Unsolved, requires new physics. But we are not just physicists, we are engineers. And an engineer's job is to take an impossible theory and forge it into a working machine. The fatal flaw in our thinking, up until this point, has been to see the Earth as the adversary. We have treated its immense pressure and energy as obstacles to be overcome. But what if that's the wrong perspective? What if the very forces that are trying to destroy us are, in fact, the key to our salvation? This is the ingenious connection. This is the eureka moment. The thesis is this: we will not fight the Earth. We will harness it. We will build a machine that turns the planet itself into a component of its own engine. Let's abandon the idea of finding or creating exotic matter in a vacuum. The energy requirements would be astronomical. Instead, let's look at the environment we're in. We are surrounded by a colossal gravitational field, a sea of energy potential. We are swimming in exactly what we need. Our task is not to create negative energy from nothing, but to coax it into existence from the fabric of space-time that is already stressed to the breaking point by the planet's mass. How? Through the principle of resonance. Think of an opera singer holding a single perfect note and shattering a crystal glass. The singer does not destroy the glass with the force of their breath. They do it by finding the glass's natural resonant frequency. They apply a tiny amount of energy, precisely tuned, which is then absorbed and amplified by the structure of the glass itself until it vibrates so violently that it tears itself apart. We are going to apply this exact principle, not to a wine glass, but to the fabric of space-time in the heart of our planet. Our vessel, let's call it the geode, will not be a drill or a submarine. It will be a musical instrument of immense sophistication. The core of its engine will not be a propeller, but a series of superconducting, oscillating rings. We will call this the resonant gravitational field modulator. This engine will not try to generate a warp bubble by brute force. Instead, it will generate a very specific high-frequency gravitational wave, a hum. This hum, the vibration of our engine, will be precisely tuned to the resonant frequency of the space-time, compressed by the Earth's core. We will be singing to the planet in the language of gravity. The geode's fusion reactor won't be powering a drive. It will be powering this hum, this initial delicate vibration. The planet's own gravitational field will do the rest. As our engine's hum propagates, the local space-time fabric will begin to resonate, amplifying the wave enormously. The immense stored potential energy of the planet's gravity well will be pumped into our gravitational wave, turning our whisper into a roar. And here is where the magic happens. This violent, localized resonance of space-time will create the conditions we need, drawing inspiration from the quantum Casimir effect, where negative energy can appear between two plates in a vacuum. Our engine will use the planet as one of those plates. The oscillating wave front from our engine will act as the other. By precisely controlling the shape and frequency of our resonance, we can create regions where the space-time vibration is so extreme that it generates a net negative energy density in front of the ship. This is the exotic matter we need. It's not a substance we carry with us, but an effect we generate in situ. This negative energy will expand space-time in front of us, while the corresponding positive energy peak in the wave behind us will compress space-time, pushing us forward. We will have created our warp bubble, a bubble made not in a lab, but forged in the heart of a planetary furnace, using the planet's own energy as the fuel. We will have turned our greatest enemy, the crushing gravity of the Earth, into our engine. This thesis redefines the entire engineering of the vessel. The geode's hull is no longer a pressure vessel designed to keep the Earth out. That job is now handled by the space-time boundary of the warp bubble. Instead, the hull becomes a sophisticated science instrument, a multi-layered composite shell whose primary function is to insulate the interior from the engine's ferocious gravitational and electromagnetic output. It is a cage for the tamed beast within. The outer layers would be superconducting, shaping the gravitational fields with perfect precision. The inner layers would be composed of metamaterials designed to warp and cancel any stray gravitational waves, ensuring the crew and instruments experience perfect 1g gravity and 0 time dilation, even as the spacetime just meters away is being twisted into knots. The power source, a compact toroidal fusion reactor, provides the spark for the resonance, but it's the planet that provides the true power. This makes the mission vastly more energy efficient than any brute force method. And this principle, this partnership with the planet, begins to solve our other impossible problems. Steering, for example. How do you pilot a warp bubble? It's not done with rudders or thrusters. It's done by being a maestro. The pilots would be tuning the resonant gravitational field modulator. By making minute adjustments to the frequency and amplitude of the different superconducting rings, they could alter the shape of the resonance and therefore the shape and direction of the warp bubble. They would be able to delicately steer the geode to the varying densities of the mantle and core, not by pushing through them, but by flowing around them on a river of manipulated spacetime. And what about communication? The most isolating problem of all. A warp bubble offers a radical, almost mystical solution. If we are already manipulating the topology of spacetime, who is to say we cannot create a stable, microscopic connection to the surface? A traversable micro-wormhole, an Einstein-Rosen bridge, just wide enough to transmit a laser beam of data. The signal would not travel through the 6,000 kilometers of interfering rock and metal. It would take a shortcut outside of our conventional space, arriving at the surface instantaneously and without degradation. We would not be deaf and blind. We would have a perfect, real-time connection to home. Our lifeline would not be a cable, but a thread woven from the very fabric of the cosmos. This is the core of our technical thesis. Stop seeing the planet as a wall and start seeing it as a battery, a lens, and a partner. This is the ingenious connection that makes the journey possible. A blueprint, no matter how brilliant, is just a dream on paper. The final act of any engineering endeavor is to transform that dream into reality. To take the complex physics, the exotic materials, and the audacious concepts and build something real. So how would we build the geode? And what would its first historic mission look like? This is not a project for a garage or even a traditional factory. This would be the single largest and most complex scientific undertaking in human history. A program that would make the Manhattan Project or the Apollo program look like preliminary sketches. The construction would require a location of unparalleled geological stability, a place where the Earth's crust is ancient, thick, and quiet, a place like the heart of the Canadian Shield, or perhaps the Siberian platform. Here, we would not build a factory on the surface, but excavate a cathedral to science deep underground, a multi-kilometer deep cylindrical chamber, shielded by meters of lead and dense rock, to house the assembly of the geode and protect the surface from the gravitational stresses of its initial activation. The materials for its construction would themselves be the product of a revolution in materials science. The great superconducting rings of the resonant gravitational field modulator, the heart of the machine, could not be forged from any conventional metal. They would likely be grown, atom by atom, from a lattice of room-temperature superconducting carbon, a material theorized, but not yet perfected, held within a composite of stabilized metallic hydrogen, a substance only thought to exist in the hearts of gas giants, now created in our labs. The hull, our shield against the engine's own fury, would be an alloy of the densest elements known, osmium and iridium, interlaced with a network of programmable metamaterials that could actively bend and cancel gravitational waves. For decades, robotic arms would glide through the vacuum of the assembly chamber, meticulously piecing together these components. The final piece of the puzzle would be the power source, a compact, fourth-generation fusion reactor capable of stellar-level energy output for centuries, would be lowered into the vessel's core. It would be a ceremony watched by the entire world, the moment humanity gave its impossible machine a beating heart. The years of calibration that would follow would be an engineering saga in itself. Millions of simulations would test every possible resonance, every potential geological interaction. Then would come the first activation, the first hum. For a single microsecond, the engine would be brought online at less than 1,000% of its power. Around the world, the most sensitive gravitational wave detectors would register a faint, perfectly tuned ping, the sound of humanity knocking, for the first time, on the fabric of space-time itself. The launch, when it finally came, would be a silent, slow, and breathtakingly delicate process. There would be no fire, no sound, no violent shaking. The geode, resting on its launch cradle deep beneath the Earth, would simply activate its warp bubble at minimal power. The security monitors would show it flicker, and then it would be gone. It would have phased a few millimeters downward, its bubble of isolated space-time now occupying a space that was, a moment before, solid bedrock. The mission would have begun. The first weeks would be an agonizingly slow descent through the crust, the pilots constantly tuning the engine's resonance, learning to play the instrument, listening to the feedback from the planet, feeling out the composition of the rock around them, not through sight, but by how the space-time fabric responded to their touch. Only after mastering this planetary symphony would they begin the true descent, accelerating into the deep, unknown world of the mantle and core. And if they succeed, if they reach the inner core, touch the solid heart of our world, and return with their priceless data, what then? The legacy of the Geode mission would unfold in waves, each one more transformative than the last. The first wave would be a revolution in science. For the first time, we would have direct, real-time data from every layer of our planet. We would understand the Earth's magnetic dynamo not as a theoretical model, but as a living, breathing engine. Our understanding of plate tectonics, volcanism, and seismology would leap forward by millennia. We could potentially predict earthquakes and volcanic eruptions, not with days of warning, but with centuries of notice, saving countless lives and fundamentally changing our relationship with the planet we live on. We would read the history of our world, chapter and verse, written in the strata of the mantle and the composition of the core. The second wave would be a revolution in resources and industry. The core of our planet is the ultimate treasure chest. During its formation, the heaviest elements sank to the center. There is enough gold, platinum, iridium, and other precious heavy metals in the core to cover the entire surface of the Earth in a 4-meter-thick layer. The geode technology, once perfected, would allow us to perform a kind of planetary-scale keyhole surgery. We could phase small, targeted pockets of these elements from the core to facilities on the surface without disruptive mining. Scarcity of these critical industrial and technological materials would become a concept of the past. It would usher in an age of post-scarcity abundance, completely rewriting economics and enabling a new golden age of construction and technology for all of humanity. The third and most profound wave of the legacy would be the moment the geode technology is turned outwards towards the cosmos. The mission to the Earth's core was never the final goal. It was the training ground. It was our Wright Flyer moment for spacetime engineering. A machine that can manipulate a planet's core can manipulate a planet's fate. The first target would be Mars. We could send a larger, more powerful geode to the red planet, not to explore its core, but to restart it. By focusing a resonant wave of unimaginable power, we could reliquefy the Martian core and spin it back into life, creating a new dynamo. Mars would generate its own magnetic field once more. With that shield in place, we could then build an atmosphere that wouldn't be blown away by the solar wind. The geode would not just be an explorer. It would be a terraforming engine, a planetary defibrillator capable of bringing dead worlds back to life. And this, finally, is the ultimate legacy. The journey to the center of the Earth was the answer to the final question of cosmic engineering. It was the key that unlocks everything else. The same drive, the same principles of resonant space-time manipulation could be used to create a warp bubble that doesn't just travel through a planet, but through the vast emptiness between the stars. The geode is the ancestor of the first starship. In a moment of beautiful cosmic irony, we would discover that the only way to truly reach for the stars was to first have the courage, the audacity, and the ingenuity to journey to the heart of our own home. To conquer the final frontier above, we first had to conquer the final frontier within. The 6,000-kilometer descent was, all along, the first step on an infinite ascent. And so, our investigation comes to a close. We began with a simple, almost childlike question. Could we journey to the center of the Earth? We stood before the ultimate locked room mystery, a vault sealed not by steel and tumblers, but by the fundamental laws of physics themselves. Our initial analysis was bleak. We examined the evidence, and every piece told the same story: failure. We saw a pressure that could atomize any known material, a heat that could vaporize any machine, and a desolate, crushing isolation that would render us blind, deaf, and utterly alone. The case file, by all conventional logic, should have been stamped impossible and filed away forever in the archives of unrealizable dreams. The planet had constructed a perfect defense, and our engineering, for all its cleverness, seemed to be a hopelessly inadequate weapon. The descent was, by every measure we could apply, a journey into absolute oblivion. But then, we did what every good detective, every good engineer, and every curious human being must do when faced with an impenetrable wall. We changed our perspective. We stopped looking at the wall and started looking for a door. And to do that, we lifted our gaze from the terrestrial to the cosmic. We looked for precedents not in our own workshops, but in the grand laboratory of the universe. We found clues in the quantum defiance of neutron stars and the space-time geometry of black holes. These clues led us to a radical hypothesis. What if the solution wasn't to build a stronger wall, but to find a way to never touch the wall at all? This led us to the breathtaking concept of the warp bubble, a pocket of serene, isolated space-time that could carry us untouched through the inferno. And this, in turn, led us to our grand unifying thesis, the eureka moment of our investigation. The revelation that the very forces arrayed against us, the colossal pressure and energy of the planet itself, were not the obstacle, but the key. Through the principle of resonance, we could coax the planet into becoming a partner, using its own gravitational might to power the engine that would allow us to explore its deepest secrets. This single, profound shift in thinking transformed everything. The mission was no longer a battle against the Earth, but a dance with it. From this thesis, a new vision of engineering emerged. We imagined the geode, a vessel that was less of a ship and more of a finely tuned scientific instrument. We envisioned its construction, a monumental testament to human ambition. We mapped out its silent, graceful descent, a journey not of brute force, but of immense finesse. And finally, we followed the legacy of that first journey to its logical, staggering conclusion, a future where we are masters of our planetary environment, where we can bring dead worlds back to life, and where the road to the stars begins with a journey 6,000 kilometers straight down. We solved the case. We demonstrated that the impossible journey was, in fact, merely a problem waiting for a more elegant question to be asked. This investigation, in the end, tells a story larger than just one machine or one mission. It tells the story of the word impossible. It reveals that impossibility is often a temporary state of being. It is a horizon that recedes as we approach it. For the engineers of the 19th century, a machine that could fly was impossible. For the physicists of the early 20th century, splitting the atom was impossible. For the dreamers of the mid-20th century, walking on the moon was impossible. Every great leap forward in human history is the story of an impossibility being slain. The weapon that slays it is always the same, a courageous act of engineering imagination. It is the refusal to accept the tyranny of the known. It is the audacity to believe that the laws of nature are not just a set of constraints, but a set of tools we have not yet learned how to wield. This is the ultimate purpose of engineering in the grandest sense. It is the bridge between what is and what could be. It is the practical application of hope. Physics may write the rules of the universe, but it is engineering that allows us to play the game. The geode, this imaginary vessel born from our investigation, is the ultimate symbol of that relationship. It takes one of the most esoteric and abstract concepts in all of physics, the curvature of spacetime, and proposes to turn it into a functional piece of hardware. It is the final and most powerful statement that there is no corner of reality, no matter how strange or counterintuitive, that human ingenuity will not eventually seek to understand, to harness, and to build with. Our journey to the center of the earth has taught us the most beautiful lesson in all of exploration. The path outward is always inward. We dream of conquering the cosmos, of planting our flags on distant worlds, but the most profound discoveries, the ones that truly unlock our future, often lie in understanding our own home, our own nature, and our own hidden potential. The geode is more than a machine. It is a metaphor. It represents the idea that by delving into the deepest, most difficult problems, by facing the most extreme challenges, we discover the keys to our own transcendence. The quest to conquer the final frontier is not just about building better rockets or faster ships. It is about building better minds, capable of asking bolder questions. The stars, it turns out, are not a destination to be reached, but a consequence of a journey that begins right here, with a deep and abiding curiosity about the ground on which we stand.